Hello again. Hopefully you watched the video on evaluating inverse trig functions. The major reason for being able to do inverse trig is so we can solve trig equations. Now, I've mentioned trig equations can be one of the more challenging things that we do in the course. Unfortunately, it's something that would be nice to do in class, but we're stuck not being able to do that. So I'm going to do my best to try to get across how to solve these trig equations over the video. So, like usual, it's always good to have a motivating question. So, had you been in class, I would have put this up or given this on a piece of paper. And basically, the question is which of the following angles given solve this equation. So the equation has a trig function in it. The equation is 2 sine x equals 1. And we're basically wondering what angles, and these are all degree measures, what angles could we put in here to solve? So if you want to think about it yourself, you could pause the video, try to see if you know which ones would work. Since you can pause and try it on your own, I'm just going to go on. So if you did try it yourself, there's actually more than one solution to this. Now, there's different ways to go about it. My goal is to show how do we come up with the solutions in an analytical way, meaning how do we solve this equation to get the answers. If you're not sure how to do that, you could at the very least try them out. In order for an equation to be true, if say this is a solution, it should work in the equation. Basically, if 30 is a solution, 2 times sine 30 should give me 1. Now, I'm going to show the calculator to verify these, though I could do them by hand, but it's probably easier to show them the calculator. I'm making sure, since these are degree measures, I'm in degree mode, and I'm just going to try them out. So I'm going to do 2 times sine 30, and according to the calculator, this is a solution. If I do 2 times sine 30, I do indeed get 1. Now, if I try 60, 60 fails. So 60 does not solve the equation. 2 times sine 60 is not 1. It's some weird decimal. You can actually find it exactly if you remember your trig values, but for now I'm just looking for solutions. So 60 is not a solution. Let's try 150. And what's interesting about this is a lot of times equations only have one solution, but this actually has another solution. 150 actually works in here. So 2 times sine 150 works. So not only is 30 a solution, but so is 150. Now I can try 330. And 330, close, but doesn't quite work. It gives me -1, so it's the wrong sign. So no good. So 330 doesn't work. Let's try 240 just to see what happens. And 240 doesn't work either. All right. So here I'm just guessing and checking the calculator. But if someone didn't give me multiple choices, how would I come up with the solution? Not only that, how would I come up with both solutions? In fact, as mentioned in the inverse video, they're actually an infinite solution to these. Now, normally they don't have you find an infinitude of solutions. They'll normally just have you find the solutions in the first cycle between 0 and 360. But my goal is to show you how we can solve such equations. And the steps I'm going to give are going to be in general. Some of you may watch this and go, oh, well, this is kind of easy at first, and want to skip some of the steps. I'm going to be very methodical because these go from being I wouldn't say they're at all easy, but they go from being easier to very difficult. So I'm going to show the steps as I'm giving them. If some of you think, oh, well, I can shortcut that, by all means, but realize that the structure I'm showing you has to do for when they get quite difficult. So these range from moderately easy to maybe moderate, all the way through. They can be very, very difficult to solve. So I'm going to show the most general solution and show the steps very methodically as best I can. So hopefully everyone has an understanding of what I'm doing. And clearly this is a video, so unlike in class, you can go back and hopefully re-go over things if you don't understand them. Because like I said, this can be complicated. So hopefully you get what's going on. So I've never really taught this on a video before, and it's not the best topic to pick to start out with, but we'll try our best. So as I usually give the goals, this goal is to be able to solve trigonometric equations. Now, there's going to be several videos because, like I said, these do ramp up in difficulty. I normally take an entire week to do this. So I'm going to make a few videos that involve how progressively making them more difficult. I believe traditionally I've done 3 days where I kind of go easy, medium, and hard. And then normally we would give some practice and maybe a quiz or something. So I can include practice questions online. Obviously, we're not doing quizzes or tests or grading anything. So your goal in this is to try to follow each video. These will be the quote-unquote simpler versions, and they will progress. So the method I'm using is to cover all of them, so hopefully they're as easy as possible for you to solve. I'm going to go through these general steps. It's some of the steps in here, especially step 1, that some people may go, well, why bother doing that? I'll skip it. But I'm going to follow these 4 steps in everything I do, because when you get to the harder ones, if you methodically go through these, you should be able to solve any problem. So get a grip on these 4 steps. I'll reference them as I'm solving the problems. The general steps are: number 1, substitute the trig function, or if there's more than one function for the harder ones, with variables. I'll show this. Basically, the trig function is kind of a complicated looking thing. It's easier to replace it with a letter. So what I'm going to do is, if I have sine x in my equation, I'm just going to call it s. If I have cosine, I'm going to call it, or cosine x, I'm going to call it c. If I have tangent x, I'm going to call it t. The reason for this is to make the equation look simpler. For some of you, at first, this may seem like a step that's not worth doing, but when they get more difficult, trust me, you're going to probably want to do it the way I'm showing it. So bear with me if you at first think, well, why do the substitution step? I'm going to show it, and as it ramps up, hopefully you'll see the use of it. So number 1 is to trade out the trig function for a simpler letter. When you do that, you'll have an algebra equation, something that doesn't have trig in it because the trig has been hidden. So step 2 is to solve that equation to get the variable alone. So after the trig function has been replaced for simplicity's sake, you're going to basically solve the equation as if you were in algebra. It's going to not have the trig in it because the trig is going to be hidden. Once you get the variable alone, you have to go back and handle the trig. So step 3 is, once the variable's alone, or variables, put the trig function back in, and then that's when we're going to use an inverse, because we'll have a trig function alone that equals something, and we'll have to solve it with inverse trig. And that's going to get us one answer. If you followed the inverse trig video, basically I showed that the calculator, or you if you know your stuff, you'll get one answer. There are more answers that work. The calculator only gives you one. So step 4 is, once you have the one angle that works, you need to find all the angles that work. Typically, we'll get 2 answers. Now it says within the given domain. I'm going to start out with domains that are 1 cycle, 0 to 360. So you want to find all the angles from 0 to 360, or in radians, 0 to 2 pi that work. Someone could change that on you, and if you had to find all solutions in a certain range, I mean, there could be lots of them. If they extended it from 0 to 720, that'd be 2 cycles. You could find 4 solutions. So it's not uncommon for these to have more than one answer. Just like the warm-up, it's possible to get, most of these will have 2 answers. Not all of them, but most of them will have 2 answers. So step 4 is to find all of the answers. So hopefully you have a grasp on this. I'll reference it as I do the examples. Now basically what I'm going to do is, I'm going to show you an example, give you one to try, show a second example, give you one of that type to try, and then do a third example and give you one of that type to try. The ones I'm giving you to try, I am not going to solve in this video, but I will attach a second video that has the solutions to the U-try problems. Now, I can't enforce anything. I'm on a video. Hopefully, you do as I say and try to solve them yourself. Just watching me do them versus you doing them makes a difference. So I will show 3, and I will give sort of a your turn with each one of them. I will give a second video that has those answers, but it's better that you try them yourself. That way you can see if you can do it, and then you can compare to what I do in the subsequent video. All right, hopefully that's clear. So let's look at my first example. So how would I actually solve the one from the warm-up? This is probably the simplest they get. All of these have a decent number of steps, even the simple ones. So hang on. I'm going to solve 2 sine x equals 1, and they'll give you a domain. So there are actually infinite answers to this. There's lots of angles that as you go round and round, work over and over and over again. They limit us from 0 to 360 and not including 360. So basically 0 all the way up to 360, not including. So I need to find any of the angles that work on this. Now we saw from the warm-up that 30 when I plugged in worked and 150. My goal is to show you, well, how would you solve this if you didn't have the multiple choices and you weren't able to sort of cheat like I did with the calculator. All right, so on the board behind me, I've got the solution. I'll talk through it, and hopefully you get an idea what's going on. So I have the steps referenced, so the circle with the number in it, like circle 1, circle 2, circle 3, it's me showing each step. So the original problem is 2, there it is, 2 sine x equals 1, and there's the domain. I want to solve from 0 to 360. Now, this step, like I said, is a step that some people might think is unnecessary or might skip it, but I'm showing it because later on it will be helpful. So I want to change the trig equation into a simpler equation that doesn't have trig in it. So I hide the trig function by replacing a variable, and that's step 1. So I just made a let statement. I said let s equal sine x. So I'm hiding the trig function by using the variable s. Instead of it being 2 sine x equals 1, sine x is being represented by s, so it makes the equation look simpler. It's just 2s equals 1. The goal then is, once you have a simple equation like 2s equals 1, it's to try to get the variable by itself. So that's why I divide the 2 on both sides. I didn't show that because, there's a lot of space I don't have. So the simple algebra, hopefully you just understand because you've taken algebra. I'm solving this by dividing the 2 on both sides. That's step 2. Step 2 is isolate the variable. So I isolated the variable. I have s equals a half. Now, the goal after you solve for s is you're trying to find x. You're not trying to find s. So I did find s. S is 1/2. Once you have the variable alone, you have to put the trig function back in. So I did s equals a half. What did the s mean? The s was originally sine x. So this is the part where you might go, well, why did I even bother doing this? But like I said, later you'll see that it's helpful. So if you skip this step and just go, oh, I could just get sine x equals a half, fine. But like I said, I'm doing this on purpose, so you'll see in the more advanced videos, hopefully. So s equals 1/2. I replaced the s back with the sine x. So the trig function is now alone. I have just sine x equals 1/2. From here, this is why I went over doing inverses, because I need to solve for what is x. In order to get rid of the sine, if sine x equals a half, x is the sine inverse of 1/2. And this is from geometry. So if I want to get rid of sine, I'm just going to put the sine inverse on the other side. Remember, it's going to give me what angle makes this happen. So now, instead of just putting the answer, because you might go, well, why sine inverse of 1/2? I can put that in the calculator and get 30, or maybe you know it if you know your table values. Sine inverse of a half, one of the answers, the answer the calculator give would be 30. Now, the reason I don't put x equals 30 is because there's more than one answer. 30 is the reference angle. Remember, the reference angle is the angle in quadrant 1 that looks like, that's basically fulfills the answer. So when you go to the calculator, or you do this in your head because it's a table value, the reference angle is what you're going to state. So I'm not going to jump and just call this x. I'm just going to say, well, this thing gives me 30, and 30 is my reference angle. Now, that leads me to coming up with more than one solution. I have stack here because basically I need to know how many answers I'm going to get. You come back up here and you go, well, I'm doing sine inverse of something positive. Sine inverse of positive 1/2. Well, that means that sine x came out positive. There's two quadrants that happens in, quadrant 1 and quadrant 2, which means there's two angles that fulfill this. There's a quadrant 1 angle, which is the 30, and then there's also a quadrant 2 angle. So you see below, how did I come up with step 4? Step 4 was find all of the answers that work. 30 is one of my answers, but I need all of the answers that work in a range from 0 to 360. So how I solve this is I think about, well, there's two quadrants, so I need an answer out of quadrant 1 and an answer out of quadrant 2. My answer out of quadrant 1 is my reference angle. So 30 solves it, and 30 is one of my solutions. So when I go to the quadrant 1, I just use the angle I got in quadrant 1, which is 30. Now, quadrant 2, I have to calculate what would 30 degrees mirror image look like in quadrant 2. Well, using the formula in quadrant 2, if I took 180 degrees and subtracted the 30, the reference angle, it'll give me what that other angle is. So what's 30's mirror image in quadrant 2? It's 150 degrees. So that's the second solution. And basically that gives me a solution in each quadrant, so those are my answers. So that's how I analytically came up with them. This part's a little tricky, but I'll show you a couple times doing it. So I should get a quadrant 1, quadrant 2 solution. My quadrant 1 solution was what the calculator gave me, but I have to realize there's a second solution in quadrant 2, which is that 150. So I'm basically finding that angle. Here's kind of a picture of what's going on. So the angle in quadrant 1 is what the calculator gave me. And then its mirror image in quadrant 2, I basically had to take that 30 degrees and subtract it from 180. So here's the 30. What's this angle? It's 180 minus the reference angle, or 30. So that's the other angle that fulfills this equation. So basically those are the two solutions. The two solutions are 30 and 150. All right, and those are all 4 steps done out. So to remind you of those 4 steps, let's go back. So you can go back and look. I substituted with a variable. I got the variable alone. Once the variable is alone, I put the trig function back in. I used an inverse trig function to find the reference angle, and then I found all angles in all quadrants that worked. So this is the one you can try. I'm not going to put the solution in this video, but I will put the solution to all the ones I've asked you to try in a second video that will be included. All right, so your goal would be see if you could answer this, and you can check your answer in the attached in the second video that's with this. So let me move on to my second example. This is similar to the other problem. Its differences, what makes it a little more difficult, is its secant. So that's one of the reciprocal trig functions. So that's one of the things I'm going to have to handle. And probably the worst part of this example is sometimes they want answers in degrees, and sometimes they want answers in radians. And especially for honors students who are watching, or any non-honors student who plans on having to take something like calculus when you go to college. Unfortunately, most higher math is done in radians, so when trig equations are solved, you have to be able to solve them not only in degrees, but in radians. The way I'm going to handle the radians is I'm actually going to do everything in degrees and then just convert to radians in the end. So the extra step will be to ignore the radians for now, and then go on and do it in degrees, and then at the very end change it back to radians. Sometimes you can get exact radian answers, other times you have to use the calculator. So this example, I'm going to need to use the calculator because I'm not going to get exact answers, and I'm not going to be capable of getting them because I have to use a calculator. The next example that I do, or the last one for this video, I will get exact radian answers, so I'll show you the difference between them. So the new stuff is how do I handle secant, and how do I express the answer in radians. All right. All right, so there you go. There's the second problem. Same steps. So I replaced secant with s, again, because it made sense to use that. So I have let s equal secant x. And I said that I was temporarily going to ignore the radians, so I decided to go with degrees. So I will do the radians in the very end that you'll see as I go through this. But right now I'm going to think about degrees. So I'm going to let s equal secant x. That makes it so the trig function's hidden. I don't see the trig function. It just looks like a regular algebra equation. My equation is 3 plus 2s equals 0. I solve that for s. So step 2 says get the variable alone. So I subtracted the 3 over, divided the 2, and I get s equals negative 3 halves. So that gets me through step 1 and 2. Once the s is alone and I've solved for that variable, I got to go back and get what x is. So I restore the trig function. S was secant x. Now, I don't want to work with secant because the problem is in the calculator, in order to get rid of it, I would need secant inverse, and the calculator doesn't have secant inverse in it. So I need to convert secant to cosine. Remember, secant is the reciprocal of cosine, so that's how I got the next step. If secant is negative 3 halves, then cosine is the flip. So cosine has to be negative 2/3. Now I can continue solving it because I can put cosine inverse in the calculator. I did cosine inverse of negative 2/3. And now the annoying thing about cosine is it does give me one of the answers, but it doesn't give me the reference angle. The answer it gives me is the quadrant 2 angle of 131.81. Remember, cosine's negative in quadrant 2, so it pumps out the first quadrant 2 angle it can find. There's a second answer. I have to get the reference angle. The reference angle is a little annoying because it, unlike the other problem, the inverse didn't give me the reference angle. It gave me a quadrant 2 angle. So what I did was, to get the reference angle, I thought about, well, this is in quadrant 2. What's its mirror image in quadrant 1? It would be 180 minus this angle. If I do 180 minus this angle, it gives me what's in here, and that's the mirror image of what's over here. So 180 minus that angle that I got from the calculator, and this is rounded to the nearest hundredth. I didn't say in the problem, but I'm rounding it because basically I can't get an exact value for this. So I got rounded 131.81. If I take that from 180, it gives me the reference angle. So now step 4 is, now that I have the reference angle and I do have one of the solutions, I have to find all solutions that work. Since cosine was negative using stack, cosine's negative in 2 quadrants. It's negative in quadrant 2 and quadrant 3. So I need a quadrant 2 solution and a quadrant 3 solution. And that's all according to stack. So since cosine was negative, I need all the quadrants where I would get negative cosines. Well, quadrant 2 is one of them, and quadrant 3 is the other. That's why I have this red one sticking out here. So these 2 angles are going to be my solutions. The quadrant 2 angle was given to me by the calculator, so I don't need to do anything with that. The reason I got the reference angle is so I could get the quadrant 3 angle. To get the quadrant 3 angle, I have to take 180 and add on that reference angle. So I have to add on that little distance in here. That distance in here is 48 degrees. So I have to do 180 plus that 48. So 180 plus the 48.19 is 228.19. Now, if this were the other problem, I would be done because I have the degree answers. My degree answers are 131.81 degrees approximately and 228.19 degrees approximately, rounded to the hundredth. The problem wanted radians, so the last step is, if you're in degrees, you need to go back to radians, because that's how I knew they want radians. They put it 0 to 2 pi. They didn't want the degree answer. They want me to go to radians. the conversion to go from degrees to radians is to multiply by pi over 180. So I'm taking my degree answers, multiplying by pi over 180, and just rounding them to the nearest hundredth. Now, the reason I'm rounding everything is because I can't get an exact answer. These are already rounded, so there's no reason to keep them exact. So I just put this into the calculator, and it converted to radians. So 131.81 degrees is 2.30 radians rounded to the hundredth, and 228.19 degrees is 3.98 radians. So this step is necessary because they wanted the answer expressed in radians. So what are my answers in radians? 2.30 and 3.98. So when you're done, you should state these x equals actual answers. So these are my final answers. If I were on a test, I'd box these. Oh, that's my answer. And that's my answer. All right. So hopefully problem 2 illustrates, number 1, how to handle a reciprocal trig function. I did secants, so there's that extra step of handling the secant, and then what to do at the end to handle radians. All right. One last example. So, there goes the computer. So, well, this is the one I was going to have you try. It's similar to what I just did. Once again, I'm not going to solve this on this video, but you should pause and try it. I will show this solution in a subsequent video. So my last example is, this one's a little more complicated. It's got trig function on each side. It's basically, I need to find the angle that if I do 5 times sine of the angle plus 3, it's the same as if I do 3 sine of the angle plus 2. Once again, they want the solutions from 0 to 2 pi. So I have this done out, and the difference in this one's not, I actually think that second one I did was probably technically a little more difficult than this. The major reason I want to show this one is the equation looks a little more complicated, but it's not that bad to solve. And I actually will get exact radian answers versus the last problem where I had to round them. In this one, I can actually express them exactly. You want to express the answers exactly when possible. In the other problem, the problem I just did, it just wasn't possible to put them exactly. But if it is, you want to, and this example will show that. All right, so move this out of the way. And here's that last example that I'm going to do. So hopefully you'll get one more exposure to doing this. I have the 4 steps labeled, so step 1's maybe a little more useful now because I'm going to let s equal sine x. So it's once again going to hide the trig function. Instead of writing 5 sine x plus 3 equals sine x plus 2, the s now replaces the sine and it makes it look simpler. It's 5s plus 3 equals 3s plus 2. Now you can solve this as if you were in algebra. You would collect the like terms. So I subtracted 3s from both sides, collected the like terms, got 2s plus 3 equals 2. Then I moved the 3 over, and then divided by the 2. So I isolated that s. That's how I got the s alone. Getting the s alone is step 2, isolating the variable. Once the variable's isolated, now I have to go back and find x. So now that the s is all alone, I can put the trig function back in. It's really sine x equals negative a half. So I'm going to use inverse sine to find what the angle is. So since sine x equals negative 1/2, when I throw sine inverse of negative a half, this you can do in a calculator, or if you really know your table values and understand the inverse video, you might be able to come up with this yourself. It's going to give you a quadrant 4 angle, but it's going to give you the negative version. So if you want to put in a calculator, fine. If you know your table values, even better. So this comes out as negative 30. Negative 30 degrees, its reference angle is positive 30, right? Because if you're going 30 degrees into quadrant 4, it would be the mirror image of going 30 degrees in quadrant 1. So even though the calculator pumps out negative 30, that's actually not one of my solutions because I want answers from 0 to 360 or 0 to 2 pi. I wish I didn't note that yet. The solutions need to be in radians in the end, but I'm changing the degrees for temporarily. This is not even one of the solutions. Negative 30 is not in the domain. So I need to use this to get the reference angle, and then I have to consider what quadrants should my answers be in. sine is coming out negative. I'm doing sine inverse of something negative. If sine's coming out negative, it means the angle must have been in either quadrant 3 or quadrant 4. And once again, that's according to stack. Where's sine negative? Quadrant 3 and quadrant 4. So I need to come up with quadrant 3 angle and quadrant 4 angle. My quadrant 3 angle is going to be 180 plus the 30. I need to go 30 degrees more into that quadrant. So I'm going to start at 180 and then inch in 30 degrees up. I'm pointing the wrong picture over here. So there's 180, go in 30 degrees. So 180 plus 30 gives me 210. That's one of my solutions. And then the other one's in quadrant 4. I need to back up 30 degrees. So I need to do 360 minus 30. So basically those red angles are the mirror images of the reference angle, but they come up with the negative value, and they're the angles that work. So those are my solutions in degrees, 210 and 330. Now, of course, unfortunately, those are the degree solutions. They're not the radian solutions. So that's what the arrow's doing. The arrow comes up here, and here are my radian solutions. The way I'm going to get the radian solutions is like I did in the last example, do 210 degrees times pi over 180 and 330 degrees times pi over 180. The nice thing now is I can actually leave these in exact form. I had decimals the last time, decimal solutions, so I was stuck with them. But 210 and 330 are actually exact answers. So when I go to multiply by pi over 180, you can throw a 1 under this and a 1 under this and multiply across. You get 210 pi over 180. 210 over 180, you can put a calculator or realize 30 goes into both of those. This simplifies to be 7 over 6. So the exact form of this is 7 pi over 6. And I didn't need to get a decimal for it. Same thing here, 330 pi over 180 is 11 pi over 6. So notice in this case, these are exact solutions. So I stated them. Now, if you did do them with decimals, I just included them to show you what you would get. You'd get 3.67 and 5.67. The trouble with that, and how would I have gotten those? You can throw this in a calculator. You can throw this in a calculator or this in a calculator with the pi button. And if you throw it in with pi, it's going to give you the approximations. It's going to give you decimals. If you leave the pi out, it'll give you the exact version. So these are the exact versions. If I throw the pi in the calculator with the other numbers, these are the rounded versions. Unless they ask for it, I would use the exact over the inexact. In math, we always prefer exact answers when possible. So the precise, exact, 100% good answers are 7 pi over 6 and 11 pi over 6. Decimal-wise, they're approximately equal to 3.67 radians and 5.76 radians. All right? So those are 3 examples of quote-unquote simple. Unfortunately, even the simple problems in trig equations are complicated because you have to go through all these steps. The big steps are getting the trig function isolated, doing the equation part of it. And then the second part, which requires you to be good at trig, is doing this trig reasoning to go back using the inverse and your knowledge of the quadrants to get the final answers for the angles. In theory, if you plug in these into the original problem, they should work. So you're solving for what the x values are. It's just a lot of work to get there. So that is, you're probably happy now if you watched all this, that's the last example for this video. I did say I would give you, well, last one I'd give you one to try. And once again, for the 3rd time, please try it, see how you do. I will put the answers in a following video. All right, so I did 3. Hopefully you try these 3 and reference the next video to see what the solutions are. Okay. Well, this was a long one, but covers a few days of material. So next time I'm back, we'll unfortunately do ones that are even more difficult. But once we get through these, this will be pretty much all the trig out of the way that we need to do.